So, quick announcement. Homework 3 is available on Canvas as of about 20 minutes ago. This is a different kind of a homework. This is not something that you will have to write code for. It's entirely on Canvas. It's multiple choice questions, and it covers everything that we've seen in the semester so far. Really, this homework is an excuse to prepare for the midterm. So think of it as part of your midterm preparation. It's like a bunch of multiple choice questions that covers everything that we've seen. And if you're preparing for the midterm, along the way, this will kind of just touch a bunch of milestones there. Speaking of midterm, there's a midterm on March 6th. That's next Thursday. It'll be in class. The duration is the exact duration of the class. Importantly, it will not be on Zoom because I don't know how that works. It's completely self-contained. You will not need a calculator or anything. You will not be asked to write code. I know some of you were concerned about that. You will not need your notes or your laptop or your phone or any of those things. So any questions about any of these things? Yes.
Two questions. Number one, for homework 3 being due next Wednesday, that's March 5th, correct? So the
Yes.
day before that.
Yes.
Question 2. It's multiple choice on Canvas. How many attempts do you have?
Good question. So you get 2 attempts. It's basically the same mechanics as your homework 0. It's exactly the same mechanics as homework 0. You get 2 attempts and we keep the highest score.
Got it.
And there may be questions where more than one answer might be right. It's multiple choice. And so I think Canvas has a way of assigning partial credit if necessary. Yes.
Till today, is that
Including today, yes. Today we'll be wrapping up computational learning theory, and this will be part of the midterm. No, it'll be shorter because you get only. It's hard to tell. It will not look like your homework, but the proof part might be in that flavor. There's a question, can we use notes for the homework 3? Yeah, sure. You can use whatever you want. It's a homework. I have no way of checking. You can't use notes for the midterm. It will be on paper, yes. And the midterm format is not necessarily, so there's another question, will the midterm format be similar to homework 3? A part of the midterm will be multiple choice questions. Another part of the midterm will be a proof type thing. So it's going to be a combination of them. Other questions? Yes. Absolutely not. Does it say that? Well, the multiple people are asking me the same question. So are there midterms on Canvas? Yeah. Yeah, no, it's in person, in class. I would like to see all of you in class at some point. So this is my way of making sure that I get to see your faces at least twice a semester. Other questions? Yes.
You doing the material on Tuesday?
No, we won't. Well, yes, so I should have. On Tuesday, my plan is to treat the entirety of Tuesday's lecture as an extended office hours. So, I can talk about stuff if necessary, but I would like it more if you come to me with questions and we can work them. Yes.
Do you have some sort of practice exam or a list of problems that is going to be on the test?
No, I try not to. I don't like doing that because if I give you a list of problems, one thing that for sure is those questions will not be on the test. So it's almost like giving you a list of questions that will not show up in the exam.
That's already.
I already posted that on, or I think Purvit posted that on Canvas. There was a message today. So think of that as your study guide / review. My plan for Tuesday is to basically go over something like that if there are no questions, but I would prefer it if there are questions. So the important point is, if you come prepared for the Tuesday's class with questions, that could help you and the rest of your class. Other comments or questions? If not, we're going to see the last part of learning theory today, which introduces a new topic called shattering and VC dimension. This is a fun sort of a extension to computational learning theory, or at least the stuff that we've seen so far. What we've seen so far is we've already seen pack learning. We've seen an Occam's razor proof, an Occam's razor result for the case where your where your hypothesis space is finite and your learner is guaranteed to produce a concept that is consistent with any data set. So this is the Occam's razor for the consistent setting. Then we saw, then we dropped the assumption of consistency. We dropped the requirement that your learner is guaranteed to be consistent with any data set. That's the setting that we saw in the last lecture. That's agnostic learning. And it turns out even there we can construct an Occam's razor result. And in both cases, the thing that matters was the size of the hypothesis space, the number of functions your learner is exploring. If that number is large, then you need a large data set to help your learner disambiguate that set. If your set of functions is small, then you don't need a large data set to find one that is that's good enough. In both cases, we were working with finite hypothesis spaces. So we have a guarantee that if the learner explores a finite hypothesis space, we have a guarantee that says about how many examples do you need to ensure that with high probability you have low error. You also have a similar guarantee for the case where your learner does not produce a consistent hypothesis. The important point is in both cases, the complexity of learning or the sample complexity, this is something that I keep talking about. Sample complexity is simply the number of training examples that your learner needs to be able to successfully learn. The sample complexity depends on the size of the hypothesis space. The reason the size of the hypothesis makes sense is because we are working with a finite hypothesis space. If you have a finite number of functions, we can at least hope to count it. What happens if you have an infinite number of functions? None of these guarantees work. Is machine learning not possible when the number of functions is infinite? Have you seen a learning algorithm that explores an infinite number of functions? Perceptron. You've implemented it. You've implemented perceptron and its variants. And the search space for perceptron is the set of all possible weight vectors. Conceptually, you can think of perceptron as finding a weight vector among all possible weight vectors that's good for this data set. How many weight vectors exist? Infinite. As many as real numbers. Infinite. So clearly, learning should be possible when the number of functions is infinite. How do we analyze the notion of learning when we have an infinite number of functions? Are there some functions that are more expressive than others? Are there some function spaces that are more expressive than others? Intuitively, the answer is yes. Imagine that my concept class is putting boxes around regions and saying everything inside is a plus, everything outside is a minus. Rectangles, just intuitively, are less expressive than complicated shapes like this, because you can create. There are, in a very loose way of speaking, there are more wiggly shapes than there are rectangles. But both of them are infinite. How can we actually say something like this in a formal way. Another way of thinking about it is, if you have a linear threshold function, you know that some functions are not, some concepts are not linearly separable. Can you give an example of a concept that's not linearly separable? XOR. So it might look something like this. If I have a plus, a minus, plus, and a minus, you cannot put a line that separates either of them. But if I'm allowed a combination of lines, maybe if I think someone mentioned this when we were talking about linear separability. What if I draw a line here and say this side is positive, and I draw another line here and say this side is positive, and my final output is I want both of those decisions to be positive. If that's the case, I'm really looking at this region here, and I've managed to, capture only the pluses. So a single line cannot capture an XOR, but a combination of lines can. How many lines are there? Infinite. How many combinations of lines are there? Also infinite. And yet one of them seems more expressive than another. So the question is there a way to say that the second thing is more expressive than the first? We need a measure of expressiveness of hypothesis spaces that's not just this number of functions, right? It turns out that we have such a way, and the answer is something called the VC dimension, the Vapnik-Chervonenkis dimension. I can't pronounce the name. I'll just say VC dimension. It's a measure of the complexity of a set of functions that behaves analogously to the log of the size of the hypothesis space. It behaves like that, and this is the thing that we're going to study today. Is the problem statement clear? For most of today's lecture, I'll be introducing the VC dimension using a bunch of examples and then stating the definition formally. And then we'll see some, at the end of the lecture, we'll see some sample complexity bounds that use VC dimension. Okay, that's the plan for today. So just VC dimension behaves like the size of the hypothesis space. It's actually like the log of the size of the hypothesis space. To get started, let's go back to this idea of learning rectangles. Imagine the target concept is a rectangle. In fact, not any rectangle, but an axis parallel rectangle, which means this is not an axis parallel rectangle. Oh, that's not even a rectangle. This is not an axis parallel rectangle. This is one. It's the sides of the rectangle are parallel to the vertical and the horizontal axis. So what I mean when I say my goal is to learn an axis parallel rectangle is, of course, this is not a function, right? It's just a rectangle. How does this become a function? I'm going to define it as the function that says, given a rectangle, all points inside the rectangle are positive and all points outside are negative. Okay, that's a function. For every rectangle, I have a unique function. The instance space, of course, is the XY plane, and any point inside this can be classified as positive or negative based on whether it's inside or outside the rectangle. Now, suppose this rectangle here is the target function that we don't have access to. Instead, we have these three data points, these two pluses and a minus. I can find many, many rectangles that only cover the pluses, right? I can think of a really tight rectangle that goes only around this. Importantly, we want a rectangle that covers only the pluses, but not the minuses. I can also think of a really large rectangle that goes around. And you can, of course, invent any number of rectangles. So let's say we pick this one. It seems to agree with the data. Now let's say I have more data points. Clearly, my guess was wrong. We need to grow the rectangle, so let's say we grow it. I'm growing the rectangle, and so far, both these, the bigger one is now consistent with all the data points that have been seen so far. I can get more data points. It just so happens that this one is still consistent, and I get one more point, and I grow it again. I can keep doing this, right? Of course, I could get negative points here, And the way I'm designing it, it doesn't matter where I get a negative, the rectangle will not change. Since I'm growing the rectangle. But the more important point here is a question for you all is, will we be able to learn the target rectangle exactly? Or will we even come close? Can we learn the target rectangle exactly? One person's shaking no. Two people no. One person seems sad, so I'm assuming it's no. Did you have something to say? Oh, that's a thumbs down. Can one of the no's tell me why? And is there a yes? Does anyone say yes? Yeah.
Because there's an infinite number of data points that you can have in this, we'll never be able to reach the exact, target rectangle. We could just keep adding data points.
That's right. Let's say let's zoom in here. Let's say I find a new point here. And so I grow the rectangle this way. But there's still a gap. And you might say, oh, maybe I just need to zoom in. Let's zoom in more. Well, I can't. How many points are between here and here? There's an infinite number of points in any real interval, which means it's an uncountable infinity. My data set has to only be a countable set. So I can never, ever, the only way in which I can possibly, the only sort of a loophole here is if I get a point exactly on that rectangle. At that point, I don't have a choice. The only way in which I can ever learn the target rectangle is if I get a data point that sits on the rectangle, but that's a very, very unlikely thing, right? So no matter how many finite number of data points you have, unless you have a point exactly on the rectangle, you will never be able to actually find the boundary of that rectangle exactly. But can you get arbitrarily close? Can you get for any epsilon, can you get within that? Possibly, right? Because you just need a point that's within epsilon. If you have, you can get close, but you may not be able to get exactly to that point, to the rectangle. Does that make sense? So then the question is, how do we know what's the difference between, let's say, the rectangle that I have drawn that's covering the data points and this one that I'm drawing here? Well, not even a rectangle, but okay, this other one that I've drawn. Those are two rectangles that are both assigning, that are getting 100% on the training data, right? Are these two equivalent somehow? Technically not, because there are instances in the instance space, like this point here is outside one rectangle and inside another, which means they will disagree. So they are mathematically, they are different functions. But can we say something about the expressiveness of this function space in a slightly different way so that we don't have to start counting every possible rectangle? Okay, that's the goal. So to answer that question, we need to rethink the expressiveness of functions and not start from functions, but start from data. So let's rethink the whole process now. Let's think about the expressiveness of functions, but starting with data points. Suppose you have two data points. And let's say we are working with linear classifiers. Now, I've not told you what the labels of these 2 points are. But no matter how I label it, could you find a linear classifier that agrees with my labeling? How many ways are there to label these 2 points? Let's say you have only pluses and minuses. You have 2 labels. I see 4 fingers. So another nodding head. So there are 4 ways. If you have circles and triangles, I can label both of them triangle, both of them circle, and one of them a circle, the other one the triangle in 2 different ways. There are 4 ways to label these 2 points. And now, let's say I'm working with a hypothesis space called linear classifiers. For each of these, can I find a linear classifier that puts the circles on one side and the triangles on the other side? For every one of these?
Find a classifier.
I saw you nodding no, so can you comment?
For each one.
For each one independently. Not all of them together. Yes. For each one independently, then it's a yes. If they have different labels, you put the line in between them. If they have the same label, you put the line beside them. So no matter how these 2 points are labeled, the set of linear classifiers contains at least one line that can correctly match that labeling. Does that make sense? It may seem like I'm being unnecessarily going unnecessarily slow here, but trust me, this will get complicated. This is a property that we assign to linear classifiers. We say that linear functions, the set of linear classifiers, are expressive enough to shatter 2 points. This is a technical term here. No matter how those 2 points are labeled, I can produce a line that perfectly matches that label. If that happens, we say linear classifiers are expressive enough, are rich enough to shatter 2 points. Okay? So maybe 2 points is really simple. Maybe let's think of more points. Let's think of 14 points. Here are 14 points. I think there are 14. At some point I counted. So can a linear classifier match every possible labeling of these 14 points? Someone who's not you or you. Someone who's not answered in the class so far. Yes. No transformations in this space. I see some heads nodding no. Well, I could label it this way. In which case, of course, there's a line. So why are you nodding no? This was a trick question that I asked. Because remember what I said. Every possible label, you're right. The question I asked was, can a linear classifier match every possible labeling to these points? This is just one. I can't just assume find one that works and say that it's going to work for every possible labeling. Maybe that's a different labeling. And here, no matter how I try to fit the line, things are not going to work. So there is at least one labeling of this set of 14 points that no linear classifier can match. Right? So there's at least one labeling that cannot be matched by any linear classifier in 2 dimensions. Then we say linear classifiers are not expressive enough to shatter 14 points. Shatter this set of 14 points. Okay. All we need is one labeling that cannot be matched. On the other hand, consider more complicated functions. If you allow all possible curves, then you might be able to separate the pluses and the minuses. So in this sense, the set of all possible curves is more expressive than the set of all possible lines in 2 dimensions. Questions? Yeah.
So we could define shattering as, or rather, a function is able to shatter data points if you can cleanly separate all possible labelings.
No, it's not a function we are talking about, a set of functions. I'll be defining shattering right now, in fact. Here's a definition. Imagine that we are given a set of functions. I'll call that h. I have a set of functions h. and I call it H because for this for the purposes of this topic, H is the hypothesis class, and we have that. And we have a set of points S. We say that the set S is shattered by the function class H if no matter how you partition the examples into positive and negative, there is at least one member of that function class that also assigns the same labels. No matter what labels you assign to those 2 points, there was at least one line that also agreed with the same labeling. There was no matter what label, how the 14 points were partitioned into circles and triangles, there was at least one wiggly curve that also can separate the points in the same way. If that happens, then we say the set of examples is shattered by the set of functions. And the intuition here is a richer set of functions can shatter more points. Wiggly curves can shatter more points than lines. Any questions about the definition? Yes, yes. There are extensions of this to multi-class and such things, but for the purposes of this, we'll only be looking at binary. So let's look at some examples. Do you have a question? Yeah. Okay. So let's look at some examples. So here's a rather simple example. The hypothesis class called left bounded intervals. So you have a line that's bounded on the left at 0 and goes all the way to infinity. And your instances are any point in this line. So this could be an instance here. Your function says, your function is completely defined by this one number a here. And basically the way the prediction is done is if your instance lies between 0 and a, the labels are plus. If it lies more on the other side of a, the labels are minus. So if your instance x is greater than equal to, or let's make it strictly greater than a, the label is minus, else that's your function. So then the function is entirely defined by the single number a. The points in the region from 0 to a are labeled as positive. The points outside the more than a are labeled as negative. It's a class of functions. It's a very simple thing, and so I can even draw it on the whiteboard. So now let's work through this thing. This is your hypothesis class, and now so you have this class of functions. This is 0, and it's an a. So if I get x here, then this gets labeled as a plus, and on the other side it gets labeled as a minus. Now, suppose let's consider we're going to now work through this question of, can this hypothesis class shatter any data set with 1 point? Or can it shatter a data set with 1 point? Remember, the definition of shattering asks for a set of points, and H, a function class. In some literature, this is also sometimes called a range space. I will never use that phrase in the class. I'm just mentioning it in case you ever encounter it. So you have a function class and a set of points. I never said that the set of points needs to be large. I can think of a set with 1 point. It's this 1 point here. So to ask whether this set can be shattered, what do I need to do? I need to consider every possible labeling of these points. How many ways are there to label this point? If you have 2 labels, 2 different ways. Either it can be a plus or it can be a minus. Let's consider the case where this point is a plus. If that point is a plus, I can find a function in the function class that assigns it the right label by putting the a on the other side. Everything inside this range, inside that shaded area, is positive, in that point lies inside that area, so it's a positive point. So if I label the set is labeled, if the point is labeled as positive, then I found a function in my function class that also matches that label. But that's not sufficient because there's another way to label that point. I can label the point as a minus. And if I label that point as a minus, then I can find another function inside the same function class that assigns that point a negative label. Right? So what this means is no matter how this set of 1 point can be labeled, there's some function in my function class that can match that set. So any set, it turns out, this is just this applies to this 1 point here, but that 1 point is not special. It could have been here. I could have made the same argument. So that means that any set consisting of just 1 point can be shattered by left bounded intervals. This is what I've done is walked you through a proof really by enumerating every possible labeling. It's a rather simple case. It's not particularly, you might think it's rather trivial. I hope you see it's rather trivial. I should not say that. Ask me questions. Yes. Yeah, it could be infinite, it could be finite, yes. But the size, the set S, we assume is countable. And for all practical purposes, we'll be assuming that it's finite. They're talking about a set of points. Let's make this a little bit more complicated. Let's go from 1 to 2. Let's say we have 2 points. Now, can 2 points be shattered? We need to consider every possible labeling of these 2 points. How many ways are there to label these 2 points? 4. So let's consider all 4 possible ways. So I can have I'm going to write the labels at the bottom. I can have both of them as plus, plus, minus, minus, plus, and a plus, minus, minus. These are the only 4 ways in which I can label these 2 points. For each one of these, now the question is there a left bounded interval that puts the pluses inside the shaded region and the minuses outside? Can I find, for the first case, what do I need to do? Where would the boundary be? So let's call these points A and B. So is it more than B, less than A? Can someone tell me? More than B. So I can make this interval, this thing here. I can say everything inside the bracket is a positive and everything outside is negative. So all the positive points are inside the thing. What about the second row? Sorry? You said something? Oh, in between, yes. So it's in between. So, once again, I was able to find a hypothesis in my hypothesis space that matches the labeling. What about the fourth case? Let's come to the third label. What about the fourth case? I don't need to draw this bracket here. Okay. To the left of A. Okay, let's think about the third case. There isn't one. I could try, but it's not going to work. That means not every possible labeling can be shattered. This is like the same situation as 14 points and a line. There's at least one labeling of these 2 points that cannot be matched by any function inside our hypothesis space, inside the set of functions that we have. We can label these points such that no hypothesis matches the labels. That's the counterexample right there. And to kind of make this proof painfully obvious, I can try labeling it. If I put the label to the left of the first point, it mislabels the second point. If I put it to the right of the I'm missing my left and right here, but if I put it on the other side of the second point, then it mislabels the first point. If I put it in between them, it mislabels both points, and there's no other place to put it. So no matter where I put that A, at least one point is going to be mislabeled. That means there is no hypothesis, there's no function in our function space that can match this particular labeling. So what we have here is that this hypothesis class of left bounded intervals, we have a proof in two parts, or not really a proof yet. We have two different statements. The first statement was sets containing one point can be shattered. If I have one point, no matter how I label that point, there's some function inside my function class that matches that label. But sets containing 2 points cannot be shattered because given any 2 points, it's possible to find a labeling that cannot be matched by your set of functions. Even one such labeling, one counterexample is sufficient. In this case, we had exactly one counterexample. So to kind of wrap up this discussion about this set of functions, the set of left-bounded intervals can shatter any set of 1 point, but they cannot shatter any set of 2 points. Questions? Maybe you're thinking left-bounded intervals are too easy. Let's make this more complicated. Let's consider unbounded intervals or intervals. Another hypothesis class. Now we have an interval A to B. Now we have two numbers defining this interval, A and B. And the way this function class is defined is we no longer care about 0. We say that points between A and B are labeled as a plus, points outside, points either less than A or more than B are labeled as a minus. Every such interval belongs to this set of functions. Just before we move on, I hope you notice that this set of functions is infinite, right? Because it's A and B can be any real number, same as the previous one. So now we can work through the same story again. Let's consider 1 point. Can 1 point be shattered? Can someone convince me that 1 point can be shattered? Any 1 point, I don't care where this point is placed. Your interval, your function space might look like a bracket. What do I need to do to show that 1 point can be shattered? The definition of shattering asks that you consider every possible labeling. So what do I do?
You have two possible labels for that. It's either plus or minus. And then you find two values, B and A, that could get that label.
Okay, let's say that what do you do when it's a plus? Where do you put the interval?
You put A and B on both sides.
Something like this. Or if you are feeling more ambitious, maybe even this. Doesn't really matter. There are an infinite number of things. As long as A and B are on either side of the point, it contains the point. That means that point will be labeled as a plus. And there's a comment on Zoom, a couple of them, basically the same answer. If the point is labeled negative, I can put the interval outside. Only points inside the interval are correct. That means that this are labeled positive. That means this point is going to be labeled negative. So the set of intervals can shatter 1 point. What about 2 points? Remember, in the previous case, 2 points did not work. What happens with 2 points now? Let's work through it mechanically. It's very easy to do this mechanically. So you need to consider every possible labeling. How many possible labelings are there? 4 of them. So let's enumerate all of them. For each of these, there's a comment on Zoom that's correct. 2 points can also be shattered because all 4 options can be expressed in the hypothesis space. I can, no matter for every one of these labelings, I can find a function. If the 2 points are both labeled plus, I'll put the interval around them. If one of them is labeled a plus, I'll just cover the plus alone. If neither of them are labeled a plus, I'll keep the interval outside. No matter how these 2 points are labeled, I can match it. But isn't that cool? In the previous case, so by the way, this means 2 points can be shattered. The set of left-bounded intervals could not shatter 2 points, but the set of intervals can shatter 2 points. This means that the set of intervals is more expressive than the set of left-bounded intervals. It can capture more concepts. It can capture this concept in particular, where the inner point is labeled a minus and the outer point is labeled a plus, which the previous one could not. Right? Okay, good. So now let's consider 3 points. If I have 3 points, here's a counterexample. If I have 3 points, what I'll do is I will label the middle point as negative and the outside 2 points as positive. Now, no matter how I try to place that interval, I cannot cover both the outside positive points and keep the negative point outside the interval. Right? This means there's at least one labeling of these 3 points that cannot be matched by the set of intervals. The set of intervals cannot shatter 3 points. It could shatter 2, but not 3. And here, sometimes people get confused. Maybe I'm needlessly being adversarial. Maybe I should not have picked this labeling. Here's another labeling that can be matched by the set of intervals. Why can't I use this to prove that it's being shattered? It's for every labeling. The definition of shattering says every partition of the examples into positive and negative must be matched. You cannot show a particular partition and say it works. You need to consider every possible partition. Even one counterexample is sufficient to show that this set cannot be shattered. Okay? Questions? Yes.
Is there a sort of, for lack of a better term, soft shattering, wherein you can have some counterexamples, or
No.
is there not really a?
There isn't. This is a combinatorial concept and there's no sort of leeway here.
Got it.
Yeah. So with intervals, we have all sets of 1 point can be shattered, all sets of 2 points can be shattered, but no set of 3 points can be shattered. Not even one set of 3 points can be shattered, because no matter where those 3 points lie, it doesn't matter whether these 3 points are -10, -5, and -1, or maybe this is 100, 200, and 300. Doesn't really matter where they lie on the number line. They have the same sort of spatial arrangement. And so the middle point, if you make it negative, you cannot match that label. And the real proof requires you to enumerate all possible 3 points. So we've seen intervals, we've seen left-bounded intervals. And you might be thinking, these are all toy functions. Nobody cares about them. We don't learn these sorts of functions ever. So let's make it more complicated. Let's actually consider a function class that you actually implemented in homeworks. Linear classifiers. I want to consider a linear classifier in 2 dimensions. A linear classifier in 2 dimensions is nothing but a half space in a plane. Remember, what's a half space? A half space is you take the space and you slice it with a line or a plane, and one side of it is a plus, the other side is a minus. So sometimes linear classifiers are also called half spaces. The reason why I'm calling this half space is these concepts of VC dimension, shattering, etc., are prevalent in the areas of computational geometry and such things. And There, these words are more common. So, can linear classifiers shatter one point? Yes. That's an easy argument, right? If I have a point, if I label it as a plus, I can put a line here and say this side is a plus. If I label it as a minus, I can just change the direction of the arrow. No matter how one point is labeled, it can be matched. Can linear classifiers shatter 2 points? Yes, we saw that before. No matter how those 2 points are labeled. Can linear classifiers shatter 3 points? No, yes. Can
No.
there's a yes. Okay, there's a comment about 4 points on Zoom, but there's also a yes. How many people say yes? How many people say no? How many people say yes? Let me ask you a question. 1 yes, 2 yeses, a yes on Zoom. So 3 people say yes. How many people say no? More people say no. So can one of the yeses give me 3 points that can be shattered? Describe how it will be. Sorry. Where do I put those 3 points? You can't give me pluses. You're giving me labels. I want the points. Can you suggest?
I guess as long as they're not in the perfect. Well, so if you have 3 points, put them in a line or a triangle, whatever you want. You can isolate one of the points. I guess unless they're in a straight line, so the straight line would be the contract.
Excellent. That's a very good point. Can one of the no's say something? Not you, because you've already said something. Yes. You always leave. You cannot, if it's a straight line, we are actually back to this setting. Right? So if it's in a straight line, you make the middle thing minus and you make the boundaries pluses. That cannot be matched. What if they're not in a straight line? What if this point is here? If I label all of them as a plus, that's easy. If I label one of them as a minus, I can draw the line in between. If I label 2 of them as a minus, I can still do that. And if I label all 3 of them as a minus, then I draw the line outside. Yeah.
Question. So can we not project it on the 3D space?
No, we're talking about in the space. Because projecting through a 3D space is equivalent to saying you're changing the set of functions. So you're given a set of functions and a set of points. You cannot apply feature transformations, because by doing that, you are implicitly making the set of functions richer. But we care about the functions that we had. Yeah.
The space didn't include points that were in lines, then you can say it's shatterable, right?
But remember, shattering is about a particular set of examples, not all possible 3 points. So with 3 points, actually the answer is both yes and no. Excuse me. There are some sets of 3 points that can be shattered if they are not in a straight line. And there are some set of 3 points that cannot be shattered if they are in a straight line. Excuse me. So this means that unlike 1 and 2 points, it's not a universally true statement. Every set of 2 points can be shattered. Doesn't matter whether, how they are configured. But with 3 points, we need to start thinking about their configuration. So with 3 points, I can enumerate all possible cases. You have either they are on a straight line or they are not. This thing cannot be shattered. This thing can be. And to say that something cannot be shattered, I need to produce a counterexample. Here's one counterexample. There's another counterexample, which is also this one. So there are two different labelings which cannot be matched by any line. Whereas to show that the 3 points that form a triangle can be shattered, I need to then enumerate every possible labeling. There's a question on Zoom. Should shattering be applied to all labelings but not all configurations? That's right. The definition of shattering assumes you're given a set of points and a set of functions, and you're asking whether the set of functions can shatter those specific set of points. So shattering is a property of a collection of points and a collection of functions. But now let's consider 4 points. There was already a comment on Zoom about 4 points. Let's consider 4 points on a plane. Can 4 points be shattered? Why?
Pretty much absolutely.
So that's exactly the comment on Zoom. Once you hit 4 points, you can create an XOR example. So you have 4 points. I can make these two positive and these two negative. I cannot draw a line. But is this the only way in which 4 points can exist on a plane? What other way in which I could have 4 points like this? What happens now? Can this be shattered? Let's still no. Why not? Yep. If you make the middle point a different label from the boundary points, you cannot separate the middle point from the boundary using just a line. Are these the only two ways in which 4 points can exist on a line, on a plane? Is there any other way in which you can have 4 points on a plane? Yes. How many of them in a straight line? All of them. You know, let's just make it a little bit weaker than that. Let's say some 3 of them are in a straight line. So let's say 3 of those points are in a straight line and the 4th one is somewhere else. We don't care. Let's say the 4th one is here. Can this be shattered?
No.
No, because this is back to the 3 collinear points case. I just make this a minus, this a plus, this a plus. I really don't care about assigning a label there. Let's just make this a plus. This cannot be matched. Is there any other way in which you can have 4 points on a plane? You can't. Let me make the argument. If you have 4 points, either 3 of them are collinear or no 3 of them are collinear. Is that a fair statement? 3 of them are collinear. And here on the top, it's no 3 of them are collinear. If 3 of them are collinear, then you make and the 4th point is, we don't care yet. You make the middle point a minus and the other 2 points a plus, and it can't be shattered. If no 3 of them are collinear, then at least if no 3 of them are collinear, then some 3 of them form a triangle. There should be a 4th point. Either the 4th point is inside the triangle or outside the triangle. And that's the only, those are the only options. So if the 4th point is inside the triangle, you make the inside point a different label. If the 4th point is outside the triangle, you get the XOR case. And no matter how, and this is pretty much the only way in which you can have 4 points on a plane. And no matter how these 4 points are spread out on a plane, you can always find a counterexample. So what did we just prove?
Can't shatter an S with 4 points.
With any 4 points.
Any-
You cannot, using
Using the half plane.
using a half plane. So what we just proved is the set of half planes cannot shatter 4 points. There's another way of making the argument here is, suppose 3 of them lie on a line, label the points outside plus and the inside minus. Otherwise, no 3 of them lie on a line, then pick 3 of them, make a convex hull. And you can work with the convex hull. Everything inside the convex hull is the boundary points are a plus and the point inside is a minus. And then there's the XOR case. So this means that 4 points cannot be shattered. No matter how you pick 4 points, it cannot be shattered. With 3 points, there are some sets of 3 points that can be shattered if they are a triangle. There are some sets of 3 points that cannot be shattered if they are a line. With 2 points, no matter how 2 points are placed on a plane, doesn't matter whether it's these 2 points or those 2 points, no matter where they are, you can shatter them. 1 point is an easy case. Shattering can be seen as an adversarial game between you and an adversary. You claim that your hypothesis space H can shatter these D points. And your adversary is now trying to defeat you by producing a label, assigning a set of labels to your points that can not be matched by your set of functions. If the adversary tries out every possible labeling, and you can always match the labeling by producing a certain hypothesis, that means that your set of points can be shattered. Otherwise, the adversary wins. The set of points cannot be shattered. The important thing here is when you're trying to prove that a set of points are being shattered, you can choose the points. Of course, you're given a set of functions. You can choose the points, but not the labels. Your adversary, who's trying to prove it cannot be shattered, gets to pick the labels. When you were trying to construct the labels, when you were trying to show that 3 points cannot be shattered by a hyperplane or by a line, 3 points on that are collinear cannot be shattered, you tried to come up with a bad example, a bad labeling. You did not consider 3 points and you did not consider this labeling because you knew that would work. You were playing the role of the adversary. You picked this assignment to the labels because that's not going to work. So shattering can be seen as an adversarial game where the adversary is trying to prove that this set of points cannot be shattered and you're trying to prove it can be shattered. Your goal is to force the adversary to enumerate every possible label. The adversary's goal is to find that one labeling that's going to defeat you, your function class. And there is, I don't know what the next round is. This is there's something important to think about here. The intuition is a more expressive set of functions can shatter larger sets of points. And the amazing thing is there are some functions, some sets of functions that can shatter an infinite number of points. But what that means is for any D, if I pick a set S that is a subset of the instance space X such that the size of S is D, that's just another way of saying I sample a finite D number of instances, then this set of functions, there are function classes that can match any labeling of those D points. And that's true for any D. That means it can be infinite. There are function classes that can label infinite number of, that can match the labeling of infinite number of points. This is like very much similar to there are function classes that can match the labeling of any Boolean function. Decision trees can do that, right? It's analogous to that. No matter how you label the points, your functions can match it. These hypothesis spaces are called unbiased. They essentially allow every possible way to label any set of points, and they can match it. So we call it more expressive. The more expressive set of functions has fewer biases. In that, here I mean statistical bias. It has fewer biases. It does not have any assumptions that this kind of labelings are not allowed. Okay, this is just a technical detail. I mean, we're not going to do much with this observation yet. That's pretty much most of what I have to say about shattering. Because now I'm ready to introduce VC dimension, which adds a layer of complexity on top. The VC dimension talks about this is just a definition of shattering. The set S is shattered by a set of functions if any labeling of any partition of the points into positive and negative can be matched by some function in your function class. The VC dimension is simply of a hypothesis space is simply the size of the largest finite set of examples that can be shattered. It's just the largest set of points, the size of the largest set that can be shattered by this function class. This definition hides a surprising amount of complexity because the complexity is inside the definition of shattering. Really, the definition of VC dimension is implies a two-sided proof. If I want to show that the VC dimension is equal to D, so let's say that if I want to claim that the VC dimension of a hypothesis space is equal to D, then I need to show that the VC dimension is greater than or equal to D and it's strictly less than D plus 1. What does that mean? If there is at least one subset of points of size D that can be shattered by your function class, then the VC dimension is at least D. At least one subset of 3 points can be shattered by a line, right? In a triangle. Not all subsets, not all sets of 3 points can be shattered by a line, but at least one set of 3 points can be shattered by a line. That means the VC dimension of lines is at least 3. No set of points of a certain size can be shattered by the class of functions. That means the VC dimension is strictly less than that. No set of 4 points can be shattered by your lines. We just proved that, right? That means your VC dimension of lines is strictly less than 4. It's greater than or equal to 3, strictly less than 4, and it has to be a natural number. So the VC dimension of lines is what? 3. The VC is of the hypothesis space is greater than or equal to 3 and strictly less than 4. We just proved both sides. That means it has to be at least, it has to be exactly 3. The somewhat non-trivial part here is this bit here, because there are some sets of 3 points that cannot be shattered. Most of you identified that. But all we need is one set. If there exists even one subset of that size that can be shattered, then the VC dimension is that much. I'm going to delete that.
But the VC of H is less than D, should that be D plus 1? Or is that just saying if there?
It should be D plus 1. In this case, these are independent. Yeah, you're right. It should have been, to show that VC dimension is equal to D, I need to show that the VC dimension is greater than or equal to D and strictly less than D plus 1. Yes. In fact, we've already proved a bunch of VC dimensions today. We showed that for half intervals, every set of 1 point, every set containing only 1 point can be shattered. No set with 2 points can be shattered. We proved that. That was the first thing that we showed. So that means the VC dimension of half intervals is greater than or equal to 1 and strictly less than 2, which means it's exactly equal to 1. VC dimension is a number, is a natural number. For intervals, we showed no matter how we have 2 points, we can shatter it because we can always find a function that matches any labeling. So VC dimension is greater than or equal to 2. With 3 points, no matter where those 3 points are, you will find these were the 3 points. You make the middle point a minus, this thing a plus. You cannot find any interval that matches it, which means the VC dimension is strictly less than 3. That means the VC dimension of intervals is exactly 2. With half spaces in a plane, that is linear classifiers in 2 dimensions, that one's more interesting. The VC dimension. So let's enumerate this from with any one point can be shattered. That means VC of that hypothesis space is greater than or equal to 1. Any 2 points can be shattered, which means VC is greater than or equal to 2. With 3 points, I can produce one set of 3 points that can be shattered. All I need is one set of 3 points that can be shattered. We have this triangle case, right? And no matter how I label it, I'm sure I don't want to repeat that. I can match the labeling. So if even one set of 3 points can be shattered, there is a single data set. Even if there's one data set of size 3 that can be shattered, then VC is greater than or equal to 3. With 4 points, I was able to enumerate this argument that said, no matter how you place 4 points on a plane, it cannot be shattered. That means VC is strictly less than 4. VC is a natural number. So the VC dimension of half spaces in a plane is 3. So every VC dimension proof has to basically look like this. To show that VC dimension equals 3 for lines, I need to construct a data set of 3 points and show no matter how it's labeled, my line, I can find a line that matches it. And then I need to argue, no matter how I place 4 points on a plane, I cannot, there's at least one labeling that for that each configuration of 4 points that can be defeated. Yes.
So VC dimension allows us for that lower bound of greater than or equal to some value. You just need to find one example of shattering.
One data set.
One
yeah.
data set that allows shattering. Then the upper bound, we need to find no examples.
We need to prove
that
that
there are no
every single configuration of D plus 1 points cannot be shattered.
If we find even one counterexample that allows shattering, then
Then VC dimension is at least that much.
okay.
Yes. So all the examples we've seen in class so far are actually rather easy ones, but the VC dimension proof is a bit involved because for the lower bound, you need to find every labeling for a data set. For the upper bound, you need to consider for every data set, you need to find one bad labeling. Ask me questions. Yes. I'll go to you first and then come to you.
Yeah, I guess it's not super clear to me. So for the half space in the plane, wouldn't the VC dimension be 2 because there is a data set of size 3 that cannot be shattered?
That's the most common confusion. Look at the definition. It's the size of the largest finite subset of X that can be shattered. That means all we need is one subset of that size. If there exists even one I say subset because it's a subset of the instance space. If there exists one subset of that size that can be shattered, then the VC dimension is at least big by definition. So among in the 3-point case, right? With 3 points, there are some sets of 3 points that cannot be shattered when they are on a line, and there are some sets that can be shattered. Because we have at least one set that can be shattered, the VC dimension is at least 3 by definition.
So there is no case in 4 dimensions that it can shatter.
With 4 points, you mean?
Sorry, 4 points.
Yes, that's right. With 4 points, no matter how you place 4 points on a plane, you cannot shatter it. And there are only 3 possible ways of doing that, and that's this thing here. No matter how I place the 4 points, I was able to find a counterexample. Actually, you were able to find counterexamples. The reason this argument is complete is because the reason this is valid is because if I consider 4 points on a plane, among those 4 points, either 3 of them some three of them are on a line, or no three of them are on a line. So the bottom part is some three of them are on a line. If some three of them are on a line, I'll make the middle point a negative and the border points positive, which cannot be shattered. This cannot be shattered. Let's consider the case where no three of them are on a line. If no three of them are on a line, then that means that some three of them form a triangle, right? If pick three of them that form a triangle, the fourth point can either be inside the triangle, which is this case here, or the fourth point can be outside a triangle. If the fourth point is inside a triangle, I make the fourth point a plus and everything a minus. If the fourth point is outside, then I have the XOR situation. So these are the only ways in which I can place 4 points on a plane. And every data set consisting of 4 points on a plane has to be one of these three cases. And in each case, I'm able to find a labeling that prevents the line from matching it. That means that every possible data set of 4 points cannot be shattered.
What if all four are the same?
4 points, when I say 4 points, it's a set. So it's a,
If all 4 points are the same label.
but that's the thing. This is where the definition of shattering comes in. For something to be shattered, every single partition into plus and minus has to be matched. Even one bad labeling means that it cannot be shattered. This takes a little bit of time to sink in. I encourage that after the class, in your time, take your time to kind of step through the process, because this is a sort of the two sides, the VC dimension greater than equal to and less than equal to are asymmetric. In one case, we need to consider a data set, every possible label, to show that it can be shattered. To show it cannot be shattered, I need to consider every possible data set, and in each of them, I need to find one bad label. It's not symmetric. And this is the most common cause for confusion in this topic here. Yes.
Is this VC dimension only for linear functions?
No, in fact, I'm glad you asked. That's a good segue into the more complicated classes of functions. VC dimension is defined for any function class, because shattering only does not care about the nature of the function, right? By the way, intervals are not linear, incidentally. There's a comment in Zoom about kernel functions in SVM, and I am a little bit reluctant to respond to that because we have not covered SVM, and there's a good chance we won't cover kernels in this class. So we can follow up on that offline. Did you have a question? Yeah.
The part about like movie, it shatters or it does shatter.
Yeah. So to show that, so if I want to say that VC dimension of H is greater than equal to D, that means I need to produce one data set with D points such that for every labeling of D points, I'll call this data set D of D for so for every labeling of D, is my handwriting moderately legible at least? Okay. For every labeling of D, there's some function H such that H of X equals the label so there's a reason why I'm going this way. So To show that the VC dimension is greater than equal to D, I need to produce one data set with those many number of points, such that no matter how you label those points, which means you need to enumerate every labeling, there is some function such that for every example, the function agrees with the label. So importantly, notice that you have every, so, and this is really just one. That means there's, I'll call it, yeah, I'll call it one. So this is a exists, this is a for all, this is exists, and so you have a alternate between universal and existential quantification. But this is one side. Let me talk about the other side of things. I'll get rid of this here. The other side is exactly the opposite. To show that VC of H is less than some D, I'm not going to put D plus 1. It's, let's say if I want to show that it's less than D, then I need to, for every data set, for every single data set with D points, produce one labeling of D such that so for, oh wow, my handwriting is that. So let me zoom in the hope that it's easier. So for every data set, call it D, with D points, I need to produce one labeling for that data set such that my classifier cannot match that labeling. Notice that there's a difference between the top and the bottom. To show that VC dimension is greater than D, I need to produce just one data set and consider every possible labeling. Whereas at the bottom, I need to consider every possible data set and produce one labeling for each one of them. At the top, I need to consider some hypothesis that agrees with my labeling. Here, I need to show that every hypothesis disagrees.
Let's say it's much more complicated for the walls because they need to consider every data set.
Often it is. It tends to be. The top one is just mechanical. You just need to enumerate. You need to, yeah, you're right. The other thing to note, if you are familiar with formal logic, is these two statements are actually negations of each other. If you're not familiar with formal logic, ignore I said anything. Okay, we are at time. If you indulge me, can I just wrap this up? I just have a minute of material more. So it turns out that VC dimension of linear classifiers in D dimensions is D plus 1, which is basically the number of parameters you have. The VC dimension of neural networks, often we've not covered neural networks, but it tends to be the number of parameters in the network. And the VC dimension of nearest neighbors is actually infinite. Now, why is all this interesting? Because going back to the whole thing about sample complexity, it turns out VC dimension behaves like log of the size of the hypothesis space. There are standard sample complexity bounds, which I don't expect you to ever remember because I don't, that look very much like the previous thing. There's a 1 over epsilon here, there's a 1 over delta here, something involving VC dimension. We'll stop here. Maybe I'll just quickly wrap this up on Tuesday before we do the review. Everything that I do on Tuesday is not going to be there for the midterm. But we can take the question offline if you don't mind. Yeah. Okay, I'll see you on Tuesday.